Hello, my name is Jesse Moeller, and I'll be talking about standardizing some Genus 3 trisection diagrams. Before I begin, I'd like to make a couple of acknowledgments. First, I'd like to thank Maggie Miller for inviting me to talk at this carbon neutral conference. Second, I would like to thank the Max Planck Institute for providing hospitality in the fall when I worked on this problem. And lastly, I did work on this problem with Román Aranda. He's a graduate student at University of Iowa. Before we get into trisection diagrams, I would like to talk about Heegard splittings. So first of all, a three-dimensional handlebody of genus G is nothing else but the boundary connect sum of G copies of solid tori, which can be thought of as a thickened graph. So here we're looking at a solid handlebody of genus 2. The boundary of this object in particular is a surface of genus 2. So if M is a three-manifold, then a Heegard splitting of M is a union of three-dimensional one-handlebodies along their boundary. So you have these two three-manifolds with boundary, and they have the same boundary, so when you glue along that, you get a closed thing. And it's a theorem due to Moyes that actually every three-manifold has a Heegard splitting. One way to see this, here we have some basic examples of Heegard splittings. So these first two pictures demonstrate the genus 0 and genus 1 splitting of S3. The left one shows S3 as a union of two solid balls, one being kind of compact and the other using the point at infinity in R3. Similarly, the middle picture shows S3 as a union of two solid tori. The third picture, while we can't visualize it as well, instructs us that S1 cross S2 is obtained by gluing two solid tori together so that the boundaries of the meridian disks are identified. After this is properly digested, you can see that the core S1 you can see the core S1 and the spheres which foliate the S1 cross S2. Okay. So a surface together with a collection of pairwise disjoint curves that cut the surface into planar pieces provides instructions for creating a handlebody. By attaching disks to one side of the surface and capping the new boundary components, which are spheres, off with three balls, we obtain a handlebody. Therefore, a surface together with two such collections of curves determine a closed three-manifold. We're going to restrict our attention to the manifolds S3 and S1 cross S2 as we've just gone over. So in light of this, we will say that a Heegard diagram is GK standard if there are K pairs of parallel curves and G minus K pairs of curves that intersect once. These splittings are therefore the genus G splittings of K connect sum S1 cross S2. And the sphere with no curves on it up here is the unique genus 0 splitting of S3. This, anytime you see this instance of dual curves, that's what we call a stabilization. Something else we need to consider, we need to be able to discuss when two Heegard splitting diagrams are, we need to be able to discuss when two Heegard diagrams are equivalent. So we allow three moves essentially. You can do handle slides, which are pretty straightforward if you buy this picture. So you have one curve pointing to another curve essentially, and you band forward along the oriented arc that you're using, and the result of that is the new curve in your diagram. So this operation doesn't change the number of curves, and actually this is corresponding to an isotopy of a disk in the three manifold. So this actually does have a topological meaning. And also you can just isotope the curves, so that's allowed as well. And lastly, we allow any surface homeomorphism of your choice. Now that we have a good foundation in Heegard diagrams for three manifolds, let's talk about trisections of four manifolds. A trisection of a closed four-manifold is a decomposition into four-dimensional one-handle bodies. Again, these can be thought of as thickened graphs, and these four-dimensional one-handle bodies in a trisection have pairwise intersections that are genus G one-handle bodies, and whose triple intersection is a genus G surface. We often think of these standard four-dimensional pieces as sitting in this pie chart with three slices of pie. And it's a consequence of this decomposition that any pair of the three-dimensional one-handle bodies is actually a Heegard splitting of the boundary of one of these four-dimensional pieces. Since these four-dimensional pieces are boundary connect sums of S1 cross D3s, these Heegard splittings have to be Heegard splittings of S1 cross S2. And so therefore they have to be slide equivalent and surface homeomorphism equivalent to one of those GK standard diagrams. So that's what we're saying here. So one of these standard pieces, its boundary is the union of these three-dimensional one-handle bodies, which again is a Heegard splitting. And we know which manifold that is going to be. So therefore, any trisection diagram that we have will be a collection of curves on a surface, the trisection surface, and pairwise they need to be equivalent to these GK standard Heegard splittings. I want to point out that David Gay and Rob Kirby are the ones who thought of trisections. They introduced trisections, and they proved that every smooth four-manifold admits a trisection. And they also proved that any two trisections of the same four-manifold are stably equivalent. So you can stabilize some number of times, and those two diagrams will be equivalent. And equivalence is in the same sense as before. So you can do handle slides and you can do surface homeomorphisms. So now I want to talk about the low genus trisection diagrams. So here we have the genus 0 splitting of S4. And here are some genus 1 splittings, CP2, CP2 bar, and S1 cross S3. If you're familiar with Kirby diagrams, then you can actually get a Kirby diagram from a trisection diagram in the following way. So pick your two favorite colors, actually slide them into a position so that they are GK standard. Then the trisection diagram can be turned into a Kirby diagram by identifying all of the common curves, turning those into dotted one handles, and then the remaining green curves can be pushed off of the surface, and you can give those the surface framing. And so that'll give you a framed link with dotted one handles present, and that will be your curvy diagram. It's a theorem of Jeff Meyer and Alex Zupan that if you have a prime four-manifold and it has a genus 2 trisection diagram, then actually it's S2 cross S2, and its diagram is slide equivalent to this nice one. Essentially, what Jeff and Alex tell us with this theorem is that these are all of the interesting trisection diagrams of genus at most 2. So it is natural to wonder which four manifolds admit genus 3 trisections. And with that, we're going to move on to defining these fairy diagrams. So the first thing you're going to want to do is pick 3 rational numbers that satisfy this determinant condition. So pairwise, when you do this computation, you'll get either 0, 1, or -1. So once you have those rational numbers, put them in your back pocket. By the way, you can get a triple of distinct rational numbers this way by looking at this fairy circle. Alan Hatcher wrote about this somewhere, I think in his Topology of Numbers book. And in any case, if you take 2 of these kind of initial points on this circle, and you add the numerator and denominator, that'll give you another rational number. And all 3 of these give you a fairy triple, which satisfies the condition that we desire. So to begin drawing the trisection diagram, we're going to start by drawing this 6 chain in the middle. So we'll refer to this configuration of curves as a 6 chain. So draw your 6 chain on your genus 3 surface. You'll have some room left over to draw these meridians, mu alpha, mu beta, mu gamma, and you'll have just enough room to fill in a longitude, lambda, which is dual to each of those meridians. Now, lambda, together with any of these meridians, the regular neighborhood of those two will be a punctured torus. And since we have 2 red curves, we have a surface of genus 3, so we need one more curve of each color. We're going to use these rational numbers to place our remaining curves. So place torus knots in those punctured torus neighborhoods. This is the triple of fairy numbers that I decided to use. So we'll place our 1, 1 curve here, our 0, 1 curve here, and our 1, 2 curve here. And in this consideration, we're going to exclude fairy triples where they're all the same, because these actually turn out to correspond to spun lens spaces, and those trisection diagrams have already been considered by Jeff Meyer in his spun 3 manifolds paper. So now that we have this combinatorial way of just throwing some curves on a surface, we want to actually check that this is a trisection diagram. We want to actually verify the pairwise sets of curves condition that this corresponds to a closed 4-manifold. So you can forget about the green curves for now, and all we have to do is check that this is slide equivalent to a GK standard diagram. So forget about the green curves, slide all of the red meridians across this middle 6-chain curve. And if you do that, it doesn't matter which curves, which torus knots you selected, it'll put the red and blue torus knots onto the same punctured torus neighborhood. And so that determinant number from earlier will now realize their geometric intersection number, which means that the red and blue curves, since two of the pairs will definitely be dual to each other, and this third one is going to be either intersection absolute value 1 or intersection absolute value 0. So that tells us that what you have left after this slide is definitely a GK standard Heegard splitting. So in total, this whole thing is a valid trisection diagram. Okay, great. We have a combinatorial way to generate an infinite family of genus 3 diagrams, and they can seem incredibly complicated if you just make these fractions really large. They get really complicated, and try as you might by hand, it's kind of difficult to show that, well, it's kind of difficult to show anything. It's hard to show that they're slide equivalent to each other for different fraction values. There's a couple tricks you can do. So one thing you can do is you can Dane twist the entire diagram along this curve lambda, and you know, that will change your fractions around a little bit. So you can make some assumptions like all of these rational numbers have to be less than 1 or something. But those types of moves don't really get you any closer to the truth. So, but it does turn out that in the case where not all of the fractions are the same, the curves, these very trisection diagrams are actually connected sums of those simpler diagrams from before. So let's go into talking about why that's the case. So the main realization that Román and I had is that this 6-chain in the center of these fairy trisection diagrams it's a lot of redundant information. It's taking up a lot of space, and it's not actually contributing very much information to the diagram itself. So we gained clarity by representing this 6-chain as a kind of attachment. So what we're going to do now is we're going to represent this 6-chain on a lower genus diagram. So what do I mean by that? We're going to take these curves here in the 6-chain, and we're going to crush them to points. So this blue curve gets crushed to this blue dot, this green curve gets crushed to this green dot, and this red curve is crushed to this red dot. And you'll notice that this red curve here, you know, it intersected some of these curves that got crushed to dots. We're going to keep the arc that that stays away from this pair of pants in the middle. We're going to keep that arc in the diagram, and that arc corresponds to this arc here. Okay, so we're keeping that information intact, and we're kind of forgetting all of this stuff. And one of the reasons that we're motivated to do this is that if there was any other stuff going through this pair of pants, we could always slide it off if we wanted to. We could always make it go away. And so this pair of pants, if you have one in a trisection diagram, it really does represent something topological that's going on. And I won't discuss that in this video, but if you'd like to see more, please check out our paper on the archive, and the link will be in the description. In a nutshell, we're attaching this pair of pants to our surface, and we're keeping track of the attaching information so that this is valid. Because we're doing that, one thing we're not allowed to do are these local Reidemeister 1 moves. So if you see this kink, you're not allowed to just pull it tight. Why? Well, that will add twisting to the picture that we don't want. So it will erase twisting that we do want. This can be thought of as a bunch of twisting that's occurring in our trisection diagram, and if you just pull it tight, then that erases several Dane twists of curves. Okay, so we have this new goal. Since we can represent this 6-chain as this kind of decomposed embedded curve uniquely, we might as well just forget about genus 3 diagrams and think about these embedded decomposed curves in genus 1 trisection diagrams. And that's what we did. I won't give the proof here, but essentially what we proved is that if you have a genus 1 trisection diagram, and if you have an embedded decomposed curve, so we're going to treat this dot as though it can slide over, so that this red curve can slide over this dot, this red arc can slide over this dot. That's what we mean by a decomposed curve. Then, if mu lambda is a basis for this torus, and alpha, one of our trisection curves, is the meridian for that torus, and if C represents some number of meridians and some number of longitudes, then what we're allowed to do, or what we demonstrate in our paper, is that you can slide C to remove all of the meridians from the curve, so that now it will end up being an immersed curve, because n longitudes in a torus is never going to be an embedded curve. But in any case, we've removed all of the meridians from the topology of this curve. And in this proof, we don't show the beta or the gamma curve, but in the proof, we're just pushing them around the entire time. We don't actually care where beta and gamma are. We know that there's at least one alpha curve because it's a genus 1 trisection, but beta or gamma could be any curves that are either parallel or dual to this red curve. It doesn't matter, because in the proof we're just pushing them around. We don't actually care where they are. All we care about is where this curve C ends up after you manipulate it by sliding and isotopy. Okay, so why is this good? Well, remember that we're in the situation where we wanted at least 2 of those fractions to be distinct. It's not hard to show that in this case we know that one of the beta or gamma curves is actually dual to the red curve. And so in this situation, you can grow this blue arc and then perform this multi-slide, and when you do that, you'll get this kind of twisted, crumpled up thing in the middle, but it's away from the red and blue curves completely. So wherever the gamma curve was, it doesn't really matter. This represents a trivial element in the fundamental group of the torus. You can get this entire thing away from the gamma curve. There's a delta curve, which separates this twisty thing from the rest of your trisection diagram. And what does that show us? That shows us that our fairy trisection diagram is a connected sum of the genus 1 trisection that we started with and this complicated, twisty genus 2 thing. But thanks to Jeff Meyer and Alex Zupan, we know that this genus 2 thing is actually the standard genus 2 thing. So the fairy trisections, where at least 2 of those fractions are distinct, are actually connected sums of simpler trisection diagrams. Thanks for watching.